BYD's new electric motor just hit 97% efficiency, and right now it is rattling the entire car industry. A normal gasoline engine burns fuel and throws away roughly 70% of it as waste heat before a single wheel ever turns. BYD's motor turns 97 out of every 100 units of energy directly into motion. You heard that right, 97%. And that is just the beginning, because the raw number is not even the wildest part of this story. If that got your attention, hit a quick like and subscribe, because this channel exists to break down the real engineering behind China's EV boom before anyone else explains it in plain English. By the end of this video, you will understand exactly why the world's biggest automakers are suddenly nervous about a motor the size of a suitcase. Picture a motor as a trusted messenger. Its only job is to carry energy from the battery to the wheel without dropping any of it along the way. For most of automotive history, that messenger has been clumsy. It drops a little energy as heat in the copper wiring. It drops more as friction in the bearings. It drops still more fighting magnetic resistance inside its own core. Every drop is energy you paid for and never got to use, sitting in a puddle on the factory floor instead of pushing you down the highway. This is where most people stop paying attention, because efficiency sounds like a spreadsheet topic. But here's the part that blows people's minds. That efficiency number is not just an engineering brag. It is the difference between a car that goes where you need it to go and one that leaves you stranded 20 kilometers short, watching the battery icon blink red on a cold night. Think about what a lossy messenger actually costs you over the life of a car. Every percentage point wasted is a percentage point of battery you had to buy, charge, and haul around. Dead weight, the motor never got to use. Multiply that across a battery pack, across a commute, across years of driving, and a boring number on a spec sheet becomes the real difference between range anxiety and never thinking about it again. Most competing electric motors sit somewhere in the high 80s to low 90s in efficiency, close to 97 only on paper, because squeezing out the last few points is dramatically harder than the first 90. Here's the detail that puts everything into perspective. BYD did not chase that final stretch by building a bigger motor and brute forcing the problem. It built a smarter one, engineered down to the level of individual atoms lining up inside a magnet. And that is exactly where this story is about to get a lot more specific, because the how behind 97% is even more interesting than the number itself. But here's the thing. As remarkable as that number sounds sitting on a page, it is still not the main event. The real engineering happens one layer deeper than any spec sheet ever shows you, down inside the motor's core, where the actual physics gets rewritten. Open up the motor, and the first thing you find is the magnet. And this is not the magnet stuck to your refrigerator. BYD engineered a new generation of high-energy magnet, codenamed N50EH, boosting magnetic performance by 18% while cutting electrical current losses by 44%. Two gains that would normally fight each other, delivered at once. Wrapped around that magnetic core sits a layer of silicon steel sliced down to 0.2 of a millimeter, thinner than a human fingernail. Here's what most people get wrong about thin metal in a motor. Thinner sounds weaker, almost flimsy, but in this context, thinner means something else entirely. It chokes off the wasted energy that normally leaks out of thicker steel as stray magnetism, energy that used to disappear as heat instead of torque. Layer on a 10-layer winding pattern that shortens the electrical path itself, and copper losses drop by another 21% on top of everything else. None of these numbers exist in isolation. Stack the magnet gain, the thinner steel, and the shorter winding together, and you get a motor that keeps almost everything it is given instead of leaking it away in tiny amounts. But a smarter core is only half the equation. The other half decides how fast that energy gets delivered, and this is where it gets genuinely clever. BYD paired the motor with a 1500-volt silicon carbide power module, running at more than 6 times the voltage in the wall socket in your home. Think of older silicon chips as a heavy iron gate that creaks open and shut, wasting energy with every swing. Silicon carbide behaves more like a screen door snapping open and shut so fast that almost nothing leaks out. BYD claims this power stage alone runs near 99.86% efficiency. Put the magnet, the winding, and the power module together, and the results show up in acceleration instead of spreadsheets. The performance flagship built on this platform, the Han L, launches from a standstill to 100 kilometers an hour in 2.7 seconds, then keeps pulling from 100 to 200 in 4.74 seconds. Supercar territory, wrapped inside a family sedan chassis. and that was just the ground-level hardware sitting inside a single component. The real question is what all of that saved energy actually buys you once it leaves the motor and starts rippling outward through the rest of the car. Here's what most people get wrong about a number like 97%. They assume it simply means the car goes further on a charge, and it does, but that is the small story. The real story is what that efficiency lets the rest of the vehicle stop worrying about. Less wasted energy inside the motor means less waste heat leaving the motor. Less waste heat means the cooling system around it can shrink because it has dramatically less garbage energy to carry away and dump into the air. A smaller cooling system means less weight bolted onto the car. Less weight means the battery does not have to work as hard just to move the vehicle itself around before it even gets to moving you and your groceries. Efficiency in the motor does not stay contained politely inside the motor. It ripples outward and quietly rewrites the entire engineering budget of the car, one component leaning on the next like dominoes. This is the part nobody talks about when they talk about EV efficiency ratings. A motor that wastes less energy is not just a better motor sitting in isolation, it is a permission slip for every other engineer on the team to build something lighter, smaller, and cheaper around it. The battery pack can shrink slightly and still deliver the same range. The brakes can be tuned differently because regenerative braking recovers more of what used to be lost as friction heat. Even the tires benefit because a lighter car wears them down more evenly. Then came the detail that changes how you should think about every EV efficiency number you see from here forward. A single percentage point on a spec sheet is never really just one percentage point. It compounds through every other system in the vehicle, quietly, invisibly, the same way a tiny leak in a water pipe eventually shows up as a massive bill nobody saw coming. That is why an obsessive chase for the last few points of motor efficiency is not vanity engineering. It is one of the highest leverage places in the entire car to spend research money. But this motor did not appear in a vacuum, built by engineers working alone in a sealed room with no competition breathing down their necks. And it is worth being honest, right now, about exactly who got here first. Tesla deserves real credit here, and it would be dishonest to tell this story any other way. It was Tesla that popularized the idea of folding the motor, inverter, and gearbox into one dense shared housing instead of three separate boxes bolted awkwardly together under the hood. Picture the old approach as carrying three separate tools to fix one job, and Tesla's approach as a single well-designed multi-tool that does the same work with less wasted motion between each step. That single decision helped drag the entire EV industry's typical drive efficiency up into the low 90s, somewhere around 90 to 92%, depending on conditions. That was a genuine leap forward, and it forced every legacy automaker on the planet to finally take electric drivetrains seriously instead of treating them as a side project. But Tesla was not the only one paying attention to that number. Then, in the middle of this year, a different Chinese automaker, Geely, pushed the entire category further, announcing a 16-in-1 integrated drive unit that its engineers claim reaches 93.8% peak efficiency, a claimed world record for a single housing that bundles the motor, inverter, gearbox, and thermal management all together. Here's the brutal catch buried in that announcement, the part most coverage glossed right over. That 93.8% measures an entire integrated drive system, not a motor's peak efficiency measured on its own. Those are two different tests entirely, and it would be misleading to stack them directly against BYD's 97% as if they were measuring the exact same thing. But strip away the technicality, and the direction is unmistakable either way. Every serious EV maker on the planet is now racing toward the exact same finish line, squeezing out fractions of a single percentage point that used to be considered physically pointless to even bother chasing. Not one company quietly working alone anymore, off in a corner. We are talking about Tesla's integrated housing, Geely's 16-in-1 record chase, and BYD's magnet-level engineering. Three completely different companies converging on the same brutal physics problem from three completely different directions, all inside the same 18-month window. And that was just the drivetrain fighting for every fraction of a percent it could squeeze out. The real spectacle was about to show up somewhere else entirely, in how fast you could refill the tank you had just made so efficient. Efficient motors mean less energy wasted moving the car once it is already rolling. But BYD's engineers also went after the other half of the equation, how fast energy gets into the battery to begin with, because a perfectly efficient motor still leaves you sitting at a charger for an hour if the charger itself is the bottleneck. Their newest flash charging system pushes up to 1,500 kilowatts through a single connector. Picture filling a bathtub with a garden hose versus an actual fire hose, and flash charging sits at the fire hose end, delivering enough continuous power to run about 1,500 household microwave ovens at once. You heard that right, 1,500 microwaves, funneled through one cable into one car. A 10 to 70% charge takes about 5 minutes under that system. A 10 to 97% charge takes about 9 minutes, roughly the time it takes to walk into a gas station, grab a coffee, and walk back out. Here's the detail engineers do not want headlined as a weakness, because it usually is one across the entire industry: cold weather. Drop the temperature down to negative 30 degrees Celsius, conditions that typically cripple fast charging almost entirely by thickening the battery's internal chemistry, and BYD's system still manages to take a battery from 20 to 97% in around 12 minutes, adding only about 3 minutes compared to a warm, ideal day. For Musk and every other rival watching this space, the bigger problem was never really about losing a single customer over charging speed. It was watching a competitor quietly close the one-gap electric vehicles were never supposed to be able to close against gasoline: the speed of a refill. Range anxiety used to be the #1 objection standing between a skeptical buyer and an EV purchase. A motor, efficient enough to stretch every charge, paired with a charger fast enough to make refilling feel almost like pumping gas, does not just chip away at that objection, it quietly removes it. If that charging math just surprised you, this channel's whole mission is keeping you ahead of the real engineering breakthroughs coming out of China before they hit mainstream headlines, so subscribe so you do not miss the next one. None of that charging speed matters, of course, if the battery pack cracks under real-world stress the very first moment something goes wrong out on the road. And that is exactly where this story gets almost unbelievable. BYD's second-generation Blade battery is built from long, flat cells packed edge to edge like books lined up on a shelf, instead of the loose cylindrical cans most competitors still rattle around inside their packs. That structural choice alone gives the pack extraordinary crush resistance, because flat cells packed tightly together brace each other the way books on a full shelf hold their shape, while a case of soda cans just crumples the moment you step on it. Cell by cell, all at once. In BYD's own nail penetration testing, the pack survives a compressive strength of 445 kilonewtons, equivalent to parking a fully loaded 45-ton truck directly on top of it without the thermal runaway that has caused so many headline-grabbing battery fires across the EV industry's early years. Then came the number that changes how seriously you should take that structural claim. A pack that can shrug off 45 tons is not a marginally safer battery. It is an entirely different category of engineering problem solved. Not just a stronger case holding the cells in place, not just a faster charge getting energy into them. We are talking about a battery that shrugs off a truck's weight, refuses to catch fire when punctured with a metal nail, and still hits 97% charge in 9 minutes on a good day. 3 separate engineering problems, each once considered a genuine breakthrough on its own, now solved simultaneously on the same production line. Here's the insider detail almost nobody outside a battery lab gets told. Most of the industry's early EV fires were never really a chemistry problem. They were a structural one, cells shifting and puncturing each other internally during a crash, before any external nail entered the picture. Solving that weakness with cell geometry, instead of just adding sensors to detect a fire after it starts, is a fundamentally different approach than most competitors take, and it happens to scale the cheapest. Because you're not adding components, you are packing the same cells smarter. And that was just the ground-level engineering, the motor, the charger, the battery, each one solved almost in isolation. The real question left standing is what happens when a company this obsessed with squeezing out waste turns loose on the entire planet, not just a single spec sheet. Here is the brutal catch nobody at BYD's headquarters wants headlined first. Being efficient on paper and being efficient on an actual road are not automatically the same thing. And the gap between those two numbers is where this story earns its honesty. In 2025, the International Council on Clean Transportation ran its global automaker ratings, testing real-world energy consumption per kilometer across 22 of the world's largest manufacturers. Tata Motors of India actually took the top spot, averaging about 106 watt-hours per kilometer, with fellow Indian automaker Mahindra close behind in second place. Tesla landed third. BYD landed fourth. The industry average across the entire ranking sat around 131 watt-hours per kilometer. That is an inconvenient detail to include in a video about BYD's engineering dominance, but leaving it out would make this story less true, not more impressive. What that ranking actually reveals is more interesting than a clean sweep would have been. BYD's motor technology is genuinely class-leading in peak, lab-tested efficiency, but real-world efficiency depends on the whole vehicle working together, the software managing every watt on the fly, even the tires rolling underneath it. Nobody, not even BYD, has that equation fully solved yet, and pretending otherwise would insult the engineers who built the honest 97% number this video started with. But that gap between lab efficiency and real-world efficiency has not slowed BYD's global march, and here is what makes this exciting for anyone watching the bigger picture unfold. As of this year, BYD's new energy vehicles have a presence in more than 120 countries and regions worldwide, a footprint that would have sounded like science fiction for a Chinese automaker barely a decade ago. In the United Kingdom alone, one of the toughest, most brand-loyal car markets on the planet, BYD has already carved out close to 4% of the entire new car market this year in a country that spent generations assuming German and Japanese badges owned that segment permanently. None of that expansion is happening because BYD is quietly subsidized into relevance in every market it enters. It is happening because dealerships in country after country keep discovering the same thing under the hood. A motor platform efficient enough to make range anxiety a shrinking problem instead of a permanent one baked into the technology itself, no matter which flag happens to be flying over the factory that built it. And that global expansion has not come cheap, which is the part almost nobody covers. To fuel the price war behind that market share growth, BYD slashed prices across 22 vehicle models last year, with discounts running as steep as 34%. Rivals had no real choice but to match, one after another, in a chain reaction across China's auto industry. Revenue kept climbing, but BYD's own net profit margin got squeezed to roughly 4%. Dominating an industry this fast is not free, even for the company doing the dominating. But here's the thing. As bruising as that price war has been, it is still not the main event. The main event is what happens when a company this obsessed with wasted energy stops holding back on raw power and shows the world how far the same motor philosophy can stretch. Enter the Yangwang U9 Xtreme, BYD's track-focused electric hypercar, built on the same foundational motor engineering as the family sedan sitting in a BYD showroom. 4 independent motors combined for 2,200 kilowatts, nearly 3,000 horsepower, roughly the combined output of 3 Formula One race cars and 1 road-legal chassis. Last year, an engineering version hit 496.22 kilometers an hour on a closed track in Germany, at the time the fastest production-based electric vehicle ever tested. This is the detail engineers rarely say out loud. Efficiency and raw power were supposed to be opposites in motor design. For as long as the technology has existed, you optimize hard for one, you sacrifice the other. BYD's engineering teams are now doing both, inside the same core motor architecture, simply tuned differently depending on whether the car commutes to an office or breaks a speed record in Germany. So here's what all of this actually means, zoomed all the way out. For an entire century, automotive engineers built an extraordinary body of knowledge around combustion, squeezing genuine efficiency gains out of pistons and fuel injection through decades of brilliant work. That history deserves respect. But it was always built around an unavoidable tax. Roughly 70% of every drop of fuel lost as heat before it reached a wheel, a tax every combustion engineer simply learned to accept. That tax is disappearing now, motor by motor, magnet by magnet, and the companies that spent a century mastering how to work around it are staring down a technology that wastes almost nothing. The real nightmare for a legacy automaker was never losing market share to a cheaper rival. It was watching someone solve the physics problem first, the one problem money cannot buy your way around. That is precisely the position Toyota found itself staring down, built on this same battery and motor engineering. Why the world's most conservative automaker chose to partner with BYD instead of racing it alone is sitting on your screen right now. Now I want to hear from you in the comments. Is a raw efficiency race like this exactly what the EV industry needs to finally kill range anxiety for good? Or is chasing lab numbers like 97% a distraction from the real-world efficiency gap that ratings like the ICCT's just exposed?